been a month already? Yeah. Time passes fast. Right. This is optimal difficulty of questions in an adaptive and static evaluations using Bandit methods. Essentially, so again, if you've not, if it was too much overload of information, let's forget that now. We start all over again. You are in an interview. I'm interviewing, the candidate is being interviewed. How should one pitch the level of hardness of questions? And you can imagine if you were doing it, if the candidate appears weak, no point asking very hard questions. You get very little information from there. If the candidate is very strong, no point asking very weak questions. This is the right level for each candidate. Right? And you want to quickly converge to that. So what is that right level? Even if you're deciding an exam, a written exam for people, if your aim is to select the top 1%, no point asking very easy questions. Right? You should ask harder questions then to help you separate them the best. So we'll see all of this now in our Bandit framework that we've been talking about. So it's the kind of thing that one thinks about generally in life, and Bandit tools seem to work very well in this setting. So this is joint work with Achal Basambu, who's at Kellogg Business School, and Asaf Zivi, who's at Columbia University. So we'll make a very simplified model, especially for this discussion. Suppose that the candidate's probability of answering a question correctly in an evaluation is P upon P plus X. If I ask a question with level of difficulty X, and suppose the candidate's intrinsic ability, which I don't know, is P. Candidate also doesn't know. Then the probability of successful evaluation is P upon P plus X. So stronger the candidate, higher the probability of correct answering. Harder the question, lower the probability of answering correctly. So do you agree that this is a nice parsimonious model? Simple enough? I mean, I could have had a more general model, alpha P upon alpha P plus beta X raised to power alpha, probability of success. Make it a 2-parameter family so it fits the data better. What's nice about this is that this is going to converge to this model as alpha goes to infinity. So this is just, higher the ability, higher the probability. I guess higher the beta, lower the probability. So, but I'll just focus on this model right now. More generally, I could have had probability of success is some function of P and X, increases with P and reduces with X. But for now, in this talk, we'll just look at this model. Probability of success is P upon P plus X. P is not known to the evaluator. Evaluator needs to decide candidate's grade. So my objective as an evaluator is not to find out what your P is, but what grade do you get? A, B, C, or D. When you're being interviewed for a job, do you make the cut or no? Right? Because that's something I can do much faster. I don't have time to figure out exactly what the person's ability is. So the way to model that is we'll have these intervals, U0 to U1, U1 to U2, UM minus 1 to UM, and the job is to figure out which interval does the candidate belong to. So questions are asked sequentially and adaptively. So first case is where we are having an interview. So sequentially and adaptively, I'm going to ask you questions. And the point is to figure out the right interval with probability of error at most delta pack algorithm, and do this as quickly as possible. So again, this is the literature I showed you on Bandit framework, which kind of fits into, which we can also view. These are all for the best arm setting, but those ideas can be adapted to this setting. So probability of success is P, lies in some interval. I'm going to ask questions here and there to figure out what that interval is. So we develop lower bounds on expected number of questions asked that hold uniformly for all delta pack algorithms. Exactly what I did earlier. Right? So let's just understand what the lower bound is going to be and then use that to come with an algorithm. So algorithm is said to be delta pack if it asks questions adaptively at chosen levels x1, x2 through x tau, stops at tau is less than infinity. It then announces candidate's grade with error probability bounded above by delta for all delta greater than 0. So no matter what the candidate's ability is, it has this property. Then we say that the algorithm is delta pack. Any candidate who comes in, it tells it's the right interval with high probability. So what's this? Okay. So we'll develop algorithms that up to a dominant term match the lower bound. That's what we'll do, just as we did before. The key insight is that only up to 2 levels of difficulty questions need to be asked to any candidate. We should not try a variety of different levels of hardness of questions. only up to 2 levels are necessary, and typically only one. For each candidate, now that level may be different from every candidate, maybe this for someone and this for somebody else, but there's only one level typically. Or occasionally there can be 2. So this is kind of not immediately obvious, right? This comes up with after doing analysis. In terms of practicality, it means that after a quick exploration, the algorithm needs to settle down and ask questions with close to 1 or 2 levels of difficulty. So the lower bound will suggest that there's only 1 level or 2 levels. The upper bound means that you have to figure out that level, so you explore a little bit, but then quickly just focus on 1 or 2 levels of difficulty. Is this clear?
What about the quantification of hardness, X? How did you determine?
That's exactly what you're doing, right? So that's exactly my point, that X is what I'm determining. And for each candidate, there's only one X. There's the right X that has to be figured out. Maybe there are 2 X's sometimes, but typically only one X, not many X's. It's not like optimal thing for you is that 20% of times I should ask you a really easy question, 20% of times the middle, 40% of times it's much harder. It's not like that. There's only one level for you. It's an easy thing to accept once it's spelled out. Okay, so we'll also consider static exams if I get time. I may not get time, in which case I'll ignore this. Large number of candidates in a written exam. So think of this as a gate exam. Fixed number n questions asked statically. So here we decide the questions up front. It's not adaptive anymore. So 2 settings one can consider. One is min-max framework with an indifferent zone formulation. Here you say, okay, I'm asking this, I'm setting this exam for lots of people. Suppose this is 90 is a threshold. Above 90, person gets an A. Between 80 and 90, the person gets an A minus. Now suppose the person gets, between 89 and 91. If the person happens to have the ability between 89 and 91, in that case, I don't nitpick. Whether I give him A or A minus, from my point of view, I'm indifferent. So those errors one is indifferent to. So that's what we mean by indifferent zone formulation. We are willing to live with those small errors around every threshold. So the threshold is 90, 89 calling it above 90 or 91 calling it below 90 is perfectly fine. In that formulation, how do we devise questions? And the second is under availability of prior distribution on population ability. So suppose from historical data, we have sheets of data on gate examination. We have a sense of how the ability is distributed, or question, etc. So with that distribution available to us, how do we set these questions up? Okay. So this is about static exam, that we find the lower bounds on probability of incorrect assignment in the min-max framework and in indifferent zone setting. So we'll do min-max framework in the sense that we'll see the maximum probability of error that amongst all levels of ability, and we want to minimize that. I probably won't talk about these things, so let me just ignore this. But this is what I meant by min-max framework, by the indifferent zone formulation, that if this is a threshold uj, I'll specify an epsilon j so that anyone in this region, if I say that they belong to this interval, that's okay. Anyone in this region, if I say they belong to this interval, that's okay. Similarly here. So some errors I'm willing to live with. And this is pre-specified. So this is what will be used. Or I can have a setting where on the ability I already have a distribution given to me from historical data. And I can use that to make decisions. But again, I won't talk much about this, so let me just ignore this. Let's come back to the sequential setting. Let me just restrict myself to sequential setting. I think too much of information overload otherwise. So probability of success is P upon P plus X. A candidate comes to me, interview is going on. We don't know the value of P. How should that interview be conducted? How should we choose different levels of hardness of questions? Right, that's the sequentially and delta back properties. Again, the picture, P is not known to me. I'll ask questions x2, x3, x1, x1, x2, x3, so on and so forth, to figure out the person's grade as quickly as possible, controlling the error of probability to delta. Through change of measure arguments that go, same stuff which I mentioned earlier, but under probability measure P, suppose the ability of the candidate lies between ui and ui plus 1 interval. It lies in this interval. Then what are the alternate hypotheses? So another probability measure p tilde, the ability of the candidate, let's say, does not lie in this interval, lies in some other interval. That's what I'm worried about, right, when I'm asking questions. The algorithm is worried that it is claiming that this guy is coming from this interval, but actually it might be coming from some other interval. So that error has to be controlled. So question hardness x can be thought of as an arm pulled. So candidate is here. I'm deciding what question to ask next. Think of as if I'm going to just choose from the finitely many levels of hardness. Then there are finitely many arms that I'm going to pull. The only interesting thing here is when I pull an arm, any arm I pull, I learn something about the person's ability, which also tells me about the probability of the person answering the question if some other arm was pulled. So it's not like they're completely independent. So there's dependence amongst them. But nonetheless, one can use this kind of bandit framework somewhat, the lower bound framework, to develop lower bounds on the effort. And the only caveat is I'm not going to assume that there are finitely many levels of questions. I'll assume that there are uncountably many. I mean, I'll allow the flexibility that there are uncountably many. But for the purpose of writing equations, let's just assume one can use summations and not integrals. So then, again from Kaufman, Kappe, and Garivier, this non-asymptotic analysis, we get this lower bound, exactly the same analysis. Expected number of times under measure P, question x is asked, times the Kullback-Leibler which separates P upon P plus x with the alternative hypothesis. Okay, now I'm looking at actually just single threshold setting. I must have said that somewhere. Anyway, for now, let's just look at single threshold setting. So this is the case where I'm just trying to decide whether a person's ability is above level U or below level U. So suppose its true level is P, and for now, suppose P is less than U, then the only guy I'm really competing with, the only alternative hypothesis that I'm really worried about is that its level is U. Anything above U will have a higher Kullback-Leibler distance here. So if I satisfy this for U, I've satisfied this automatically for all values of P, for all values here which are bigger than U. So this, I wish I had a board I could tell you in more detail. But remember, earlier I had infimum here over all alternative hypotheses, nu in A complement. All the nu's correspond to the person's ability being higher than U. And my point simply is that if I can separate U, the worst case there is just U. This will always achieve the infimum. That optimization problem, every other solution will be higher than the solution I get when I put U here. So I'll only worry about this. That makes my life much simpler. So this is the constraint I get. It's a single constraint that I get in this case. And I want to now, see what it tells me about the bound on number of times question should be asked at level X. So all of this generalizes when X can take uncountably many values. Right now I'm just assuming it takes finitely many so that the summation and all is valid. Okay, so what's a linear program that I get? I'll make a variable here, I'll call it T of X. I want to minimize the total number of questions I ask, so summation T of X. And any delta pack algorithm has to satisfy this constraint, so this constraint should hold. T of X into Kullback-Leibler between P upon P plus X, U1 upon U1 plus X. This summation should be greater than or equal to 1. This is my linear program that I get when I'm searching for lower bound. Right? Every delta pack algorithm satisfies this constraint. So I made this variables, and I'm looking for the variables which satisfy this constraint and take minimum value here. This will give me my lower bound to the problem. What's nice is, unlike the problems which I showed you earlier, where I had an infimum here, in this case I only have a single constraint. This should be U here, just a single constraint. So for a single threshold U1, this is my problem that I want to solve. And you can see what's going to happen. It's a straightforward linear program. I want to minimize this summation. All these TXs have to satisfy this. Essentially what I should do is find the largest value of the Kullback-Leibler distance and set that Tx equal to 1 upon that largest value. Set all the other Tx's equal to 0. Is this clear? This is a linear program I'm trying to solve. I want to minimize this summation. These are all my constants times t of x. The solution is straightforward. Just find x star which maximizes this guy. Kullback-Leibler p upon p plus x with u1 upon u1 plus x. And set your tx equal to 1 upon that Kullback-Leibler distance. Remaining tx's, just set them to be 0. Because the point is, if you look at summation t of x star, I don't know what I've written down here. This summation should not be there. T of x star should just be given by this term here. The point is, this constraint, if I take a maximum value here, then this term is dominated from above by the maximum value here times summation t of x. So that means summation t of x times the maximum value here is always greater than or equal to 1. Right? So any summation t of x is always greater than or equal to 1 upon this guy here. And now I'm telling you one solution which actually achieves this. Big picture, forget the details. The solution is ask only one question in this case. And what should that question be? The question which gives you the maximum value of Kullback-Leibler between p upon p plus x and u1 upon u1 plus x. So the point is this: if I'm going to ask you questions at level 1 at fixed level x, then I get a separation between how much effort it takes. It's really measured by this Kullback-Leibler distance, p upon p plus x Bernoulli, u upon u1 plus x. Let me choose the question which makes it the easiest for me to separate you, find out your level, find out that you are separated from you. So that's achieved by this x star here. Okay, so yeah, I guess I didn't probably motivate this very well. So it would have been nice if I had a board. But the point simply is, if there's one threshold that I want to separate the question, if I want to decide the person has ability P, if I want to figure out whether it's above you or below you, what I should do is just ask questions at this level. If its level is P, the threshold is U1, find the X which maximizes the Kullback-Leibler distance. And that's the level at which I should ask questions. Now what happens when there are two levels? Say U1, many levels. Suppose P lies in some interval U1 and U2. It will lie in some interval, let's call that U1 and U2. The point is then I'll only get two constraints here. One corresponding to U1 and the other corresponding to U2. So the person's level is P, it lies between U1 and U2. I'm worried about the fact that it may actually lie, yeah, go ahead. Yeah.
Here, P is unknown, right?
P is, for the lower bound purposes, we say to ourselves that if the level was P, which is in some interval, what do points which are outside the interval, what constraint do they impose upon the amount of effort I should spend at different arms? So you can assume that P is known in that case. That's your question, right? That P is unknown.
Yes, since P is unknown, how can we compute the Q diversity in this?
No. This is for the lower bound purposes. So for that, you assume that P is known. If the level was P, what are the alternative hypotheses telling me about how many times I should sample different questions to separate at level P with respect to those other guys? So for lower bound purposes, you can assume that P is known. So let me just again state this. Let's go back here. The level is P, and suppose P is less than U1. So we are trying to say, how many times should we ask different questions? How many times should we ask questions at level x1, x2, so on and so forth? What we are worried about is that when we ask these questions, we may conclude that the person's level is above you. Right? Now, when we say above you, it could be much above you. But those are easier problems. The real problem we have to worry about is when the person is at level U. So really, our competition is the person's level P or is at level U. So that tells us that, so let's just go back further, that the number of times I should ask question X This is the lower bound analysis tells me that it should satisfy this inequality, the Kullback-Leibler between p upon p plus x and u upon u plus x, times the number of times I've asked question at level x. This summation should be greater than this level, log upon 1.2.4 delta. This is the equation I get from that likelihood ratio considerations, the delta pack considerations. Because in delta pack, you're worried that you might conclude that the level is above u, but it's actually p. Now, this is the constraint I'm worried about. What is the lower bound that I get on this EPN of x? Well, that just tells me that I have to solve this optimization problem, minimize summation t of x, subject to the fact that I have this constraint here. So it's just a single constraint here. So what should I do? The solution to this is just make t of x, just only one value positive, where this guy is maximized. Wherever this guy is smaller, gives t of x equal to 0. So just ask one question at the level, question at level x, which maximizes this distance. So that's the only question to ask, basically. So this was for when there were one threshold. If there were two thresholds or two or more thresholds, so person's level is p. I'm trying to get a lower bound. What am I concerned with? Maybe somebody below u1, maybe its actual level is below u1, and I thought it was p. So that gives me one constraint. Sorry. That gives me this constraint here. Again, anything below u1 is dominated, in the sense that that's an easier problem compared to when the level was exactly u1. So I just get this one constraint here. And similarly for levels above u2, I just get this one constraint here. In the sense, if this is true at level u2, it's automatically true for all levels u above u2. Because the Kullback-Leibler for value u above u2 will only be bigger. So this will be automatically satisfied. The point is this. This is probably worth understanding. Even if there were many, many grades, the only grades that I'm really worried about in coming up with lower bound is one which u is above p and one where u is below p. So u1 gives me one constraint, u2 gives me another constraint. All the other levels don't matter. If I separate myself, I'm worried that the level is, I'm claiming that the guy comes from in interval u1, u2, but maybe it comes below u1 or maybe it comes above u2. Those are two things which are bothering me as an algorithm from delta pack considerations. And those considerations give me these two constraints. So now I simply have to solve this two constraint linear program to decide how much, which arm should be sampled more. How much, which level should I ask my questions? What my t of x should be. So what that also means, if you understand linear programming, is that only two t's need to be positive. If I have two constraints, my optimal solution needs only two variables to be positive. All the others can be 0. That's just a standard fact in linear programming. So can restrict to at most two tx's positive. And now I can do the same trick which I did earlier. I'll take this summation of t of x, divide on both sides. Summation t of x, divide on this both sides. So minimizing this is same as maximizing the right-hand side on both sides. And actually maximizing the minimum of the right-hand side on both sides. Because these things are greater than, the minimum will be greater than, will be below both of these things. So what I get is, the max-min problem. As this is equivalent to solving the max-min problem, where I'm looking at weights w's to give to these questions. And since I've already decided that I'm only going to ask two questions, so let me just look for two levels, x1 and x2, which I'm going to ask questions. So these become variables. So I want to give weights to these two questions in such a way that the minimum value of this that I get, suppose I give weight w to question 1 at level x1 and 1 minus w to question at level x2, minimum of these two should be maximized. So this is just a notation that I've used for Kullback-Leibler p upon p plus x, u1 upon u1 plus x. And this is similarly for the other level. This I is equal to 1 and 2. So I look at minimum of these things, I want to maximize that. Let me see if I can give an intuition to this. So I'm going to ask questions at two levels. And the question is, should I say 75% at, 75% at one level and 25% at the other level? What should my proportions be? Essentially, I'm worried about separating with this threshold U1 and separating with this threshold U2. I want to control both of these errors. Okay, so what's the nice thing to be said here? The nice thing to be said here is that I could have looked at this linear program and looked at its dual and solved that instead. If you know linear programming, then you know that these duals are easy to form. So that dual just turns out to be, so now I'm calling this as KU1x, and I'm calling this as KU2x. So the dual just becomes maximize y1 plus y2, y1 times KU1x plus y2 times KU2x should be less than or equal to 1. So again, let's just go back. y1 corresponds to this constraint, y2 corresponds to this constraint. Each level x gives me a constraint. I fix a x, y1 times this Kullback-Leibler plus y2 times this Kullback-Leibler must be less than or equal to 1. So that's what I'm getting here. y1 times Kullback-Leibler at x plus y2 times Kullback-Leibler at x. This should be less than or equal to 1 for all x. So y1, y2 should satisfy this, and I'm looking for maximum y1 plus y2 which satisfy this. Again, I can do the same trick. I can divide these y's by y1 plus y2, and this optimization problem now becomes minimum. So y1 upon y1 plus y2 I'm calling as lambda. So minimum over lambda between 0 and 1, which minimizes the supremum of these values. Because this should be true for all x, this should be less than 1 upon y1 plus y2. So basically, maximizing this thing is same as minimizing 1 upon y1 plus y2, which is minimizing the highest value of this guy. So a lot of this stuff is going on, but I just want to say some nice things to you in this. I'll stop after that. The dual gives me this min-max problem. Minimum lambda 0, 1, so that this supremum is minimized. The primal was maximized with this W so that this minimum is maximized. Let me just show this to you pictorially what's going on. So this is the dual problem pictorially. This constraint gives me the Kullback-Leibler distance correspond as a function of x corresponding to U1. This gives me Kullback-Leibler distance function of x corresponding to U2. So when I ask questions at level x, constraint U1 gives me this much separation, constraint U2 gives me this much separation. So I worry about minimum of these two. I want to maximize the minimum. So it turns out that if indeed one function dominates the other completely, I should ask questions only at one level x star. So all I'm saying right now is as follows. What I've done is I have said if I ask questions at level x, what's the Kullback-Leibler separation with threshold U1, and what's the Kullback-Leibler separation with respect to U2? So I get these two values. Let me just go back here. Let me show it here instead. Sorry, this is not, before I come to this, let me just come here. So I'm going to look at okay, let me put it here. I'm looking at a convex combination of these two functions. So, lambda times one function and 1 minus lambda times the other function. I look at the convex combination of these two functions. I look at the x which optimizes this convex combination. And I'm looking in the space of all convex combinations, I want to choose the one which minimizes the maximum value of this supremum function. So if I take these two curves here, I give maybe half a way to this curve, half a way to this curve. So I look at the half times one curve plus half times the other curve. I get some curve. I look at its highest value. Amongst all convex combinations, I look for the one which minimizes the highest value. So in this case, you can see what's going to happen is, if I take these two curves, just trying to remember now. Any convex combination of these two curves at this level value of x will be more than this, right? If I take this lower curve and this upper curve, maybe I take 20% of this curve, 80% of this curve, or 50% of this curve, or 50% of that curve, the supremum value, the maximum value of the combination will be more than this. Because at this point, I'm taking a combination of this value and this value, it has to lie between these two. So my answer is always going to lie between these two. And the best thing to do is just pick this curve. Just give all the way to this curve. Because then I get the lowest of this value. So all I'm saying is, in this case, where one curve, one Kullback Leibler completely dominates the other Kullback Leibler, the best thing is to do is just to ask one question, ignore this separation at all, altogether. If you worry about candidates which lie at this threshold and ask question which separates you from these candidates, that automatically will take care of these candidates. So you don't have to worry about these. So this is a scenario where I should just ask questions at one level of hardness corresponding to one threshold, because that automatically ensures that I'll be separated from the other thresholds. This was the case when one picture completely dominated the other picture, at least when the maximum one function was dominated by the value of the function evaluated. If this function has a maximum at this point, the value of the other function at this point was higher. In that case, I just worry about this function and ask questions at this level. Now there could be pictures like this where one function looks like this and the other function looks like this, and now my dual tells me that I'm looking for a convex combination of these two functions. Every convex combination will have a supremum value. I want to look for a combination which minimizes the supremum value. So that's my task. So is this kind of clear? It's been a little bit kind of difficult to explain, but the big picture is I have two curves. I'm going to look for a convex combination of these two curves. Half times this plus half times this, I get a combination. I get another curve. That will have a largest value. I'm looking for a convex combination which minimizes the largest value. So a convex combination of these two curves may look like something like this. It may be bimodal. It rises up here, comes down, rises up here, comes down. I'm looking for a convex combination which has the minimum supremum value. So one can come up with sufficient conditions where this minimum will actually be achieved at this point. See, because at this point, if I ask questions at this level, every convex combination also has the same value. Right? So this is definitely a lower bound. But you can actually come up with sufficient conditions where this will be the optimal value. In the sense, any convex combination, there will exist a convex combination where this is the largest value. So, this will always be greater than or equal to this point. And if you can come up with one curve for which this is the largest value, then this is the optimal value. Because you're trying to find the minimum, it's always more than this. If you find one value for which this is the optimal thing, then that's the answer. So what this tells you is that for large number of problems, so my candidate is P. If I'm separating from U1 level, I get one curve. If I'm separating from U2 level, I get another curve as a function of hardness. For many of these curves, the best thing to do would be to ask at level X star, so that I'm equally, my probability of making both the mistakes is the same. Mistaking the candidate with U1 is same as mistaking the candidate with U2. It's like the candidate can is actually of grade, say, B, but mistaking him to have grade A or mistaking him to grade C has equal probability. So I ask questions at that level. So often that's going to be the case. Occasionally, in extreme cases where U1 and U2 are very far apart, and experimentally we saw when U1 and U2 are a level of like 1:20. I'm testing for whether the person is below level U1 or whether it's greater than 20 times U1. In that case, you will find functions which are bimodal. So the optimal value is going to be achieved by a bimodal function like this. And then you should ask questions at this level as well as this level. So in that case, you ask two levels of difficulty. But typically, you ask one level of difficulty. So that's kind of the big picture message that one gets from here. This is what I'm showing you is right now a dual picture. In the primal picture, it boils down to you're trying to find two levels of hardness, x1 and x2. You're just trying to put, ask two questions at level x1 and x2, so two values you want to find out, with the property that if I fix x1 and x2, and now I join this line here, a line at x1 where this function is, with line at x2 where this function is, I join them. And similarly, for the other function, evaluated x1 and evaluated x2, I join them. Now this means this is a convex combination at x1 and x2. So I'm trying to maximize the minimum. So this is minimum of these two. So this is the line. At level x1, I'm looking at minimum of these two. So I'm looking at this point. At this, I'm looking at this point. I'm trying to look at the convex combination of these 2 points, which maximizes minimum. Essentially, it means you look at this lower envelope and see the point where this lower envelope is optimized. You're looking for this point. So very pleasing graphical interpretation, fixed level x1 and x2, draw these 2 lines. Wherever they meet, that solves this problem. So now you're looking for x1 and x2, which maximizes this point. So is this kind of, at least graphically it's pleasing that the primal has this nice interpretation that you're looking for points x1 and x2, so that once you fix them, you draw this line, you find a point where they meet. That point you want to maximize. Space of x1 and x2, which maximizes this. Often that's going to be exactly this point here. Occasionally it'll be achieved at 2 separate points. And that's how you get those 2 solutions. So what's nice about all this is that you get this pleasing graphical interpretation. Both dual and primal have a different story to tell. One bounds the other, but they're not exactly related because this is not linear programming duality. This is, you modify a linear program to get the other program, and the duality is in that space. Okay, I think, let me just, so what's the algorithm going to be in this setting? It's going to be a similar thing as what I said to you earlier, that your lower bound tells you what questions to ask. So you kind of typically explore a little bit and ask at that level. Let me end, it's too much detail at this stage. So just, let me say a few things to you, very broad picture thing, that suppose I was designing a static exam. So this is a, so there are many thresholds here. I'm making this written exam for many people. I want to find out which grade they have, are they in this region or this region or this region. This is my indifference zone. I'll ask my questions with the following property. Suppose there was only one threshold U. So someone, when there's a single threshold U, the question I should ask should be exactly at level U, at that level. Meaning, so the point is this, I'm interviewing you, or I'm having a written exam, or let's say this is a big exam. I want to just select all the people who are level above level U. So what should my question be? What level of hardness? Turns out that should exactly be at level U. What should my X be? It should be exactly at level U. That's where I get the maximum separation. Basically, I'm worried at that time that I'm going to make a mistake with people who are below you or above you. These are the worst case people that I'm worried about. If I take care of them, then all the others are automatically taken care of. For those people, the best thing to kind of, to separate them correctly with fewest number of questions is to keep the question level at level U. When the indifference parameter is epsilon fixed, meaning if my grade is 90 to 100, and I'm indifferent between people lying between 89 and 91, and for the grade between 80 and 90, I'm indifferent between people writing between 79 and 81, and from 50 to 60 grade, I'm different from 49 to 51. In that setting, when my indifference zone is the same, no matter what the value of the marks is, what I should do is just ask questions at the level of the highest threshold. So meaning, I should just cater to the person at the level 90, between 89 and 90. Because As a percentage, that difference is very small, 89 to 91. I'm going to make the maximum mistakes there. So it's those people I'm most worried about. So is this kind of clear that the question I'm asking is, how hard should I make a question when I have this formulation that I don't worry about people plus minus 1 at any grade, whether it's level 10 or 20 or 30 or 40 or 50 or 60 or 70 or 80 or 90. 0 to 100 is the overall grade. So then the answer is, if I had to ask one question, it should cater to people at level 90. Because I'm much more likely to confuse person who's at 89 or 88 to be above 100, to be above 90, or 92 to be below 90, than I am to confuse people who are below level 8, somebody who's below level 8 and I confuse them to be above 10. Or somebody who's above level 12, I'm confuse them to be below level 10. So, I have to worry about the top guys much more. The remaining guys will automatically be taken care of. Okay, I think lots of pictures here, but let me just end my story right now. So we consider the interactive setting where a candidate is probed sequentially to determine the interval that contains its ability. We develop lower bound on delta pack algorithms and develop an algorithm that matches the lower bound. So that's all I've discussed right now. Let's stop with that. Thank you.